Hi, everyone. Welcome to Lesson 1, Day 3. Today, we're going to look a little bit different at functions, and let's go over our learning target one more time. I will be able to define and identify a function. So previously, we looked at relations and functions and symbols, and we're going to do a quick review on that. But today, we're going to look at function rules and what do the rules or laws need to look like to be or not to be a function, as well as the graphs. How do we tell if a graph is a function or not? As well as create diagrams. So we started with mapping diagrams, and now we're going to move into more tables and graphs, which are still types of diagrams to put our input and output values together. We're still within the same learning standard in our frameworks to make sure that we do fully encompass all of that learning standard. So moving forward into our next slide, today is going to be a lesson where you're going to take notes and see all the new vocabulary words and symbols that we use to define function rules and graphs. And tomorrow will all be your practice based on today's. So like always, please make sure you have a pencil and paper with you. You will be showing me your notes at the end of this period as well as tomorrow in class. You need to have your notes with you so that you could use those. You can ask questions about those. When do we use symbols or not symbols? What does this vocabulary word mean? Realistically, those notes help you individually process the new vocabulary and the symbols that we use. And that's a really important step in learning, is to write down, to read, to hear, and to apply. And that application will happen tomorrow in school. Make sure you have that pencil and paper. So we're going to do a quick review of our previous lesson. What is a relation? And a relation, remember, is when you have two different sets, and we're going to use the input and output as our two sets, and we collect those as ordered pairs, and each of those ordered pairs need one element from the input and one element for the output. Remember, that is our ordered pair XY. X values are our input values, Y values are our output values. Now remember, when we list our input values, we need to do it in braces. This gives us set notation, and we do it in numerical order. So here is just a set of 4 input values. For output values, remember there is a function machine where I'm putting these 4 values in. Something is happening inside that machine, and out comes the output values. Remember, the output values as well need to be in braces in numerical order. So we don't really know by looking at your input and output what matches what. The mapping diagram really helps us build that relation. And remember, we need to do that in order to show the relation. And the relation, remember, is a collection of ordered pairs in set notation. So we use our braces, and then we list all of those ordered pairs that come from the function. So in this case, these are my ordered pairs that were put into the machine and came out of the machine. And I don't know realistically what's happening in this machine yet. I have some hypothesis when I look at these different input and output values, but we're going to look more into the function rule today. Remember, input values have 3 other names. We can call them X values, independent variables, or domain values. And again, output values as well are called the Y values, the dependent variables, or the range. And most often, we're going to try to transition you into using the words domain and range instead of input and output. This is the high school terminology that you will be seeing next year. So we're going to bridge that in to your vocabulary. Remember, most important thing about relations, input and output lists is to make sure they start with braces. Your braces are located on your keyboard to the right of the letter P. You will notice there are braces and brackets on those 2 keys. To get the braces, you're going to have to hit Shift first to make sure that you have the braces on either side. So that's a quick review of what our relation was. And now let's look at what the function was, because again, we have to take our knowledge from our previous lesson and move forward with it. Remember, a function is a relation that has a set of input and output values, but the specialty about a function is where each input is related to exactly one output. So we looked at that I gave you a relation, and then I would ask you if it was a function or not, and you had to do a couple things. We listed the input values, so we looked through that relation, and we took all of the x values in numerical order and made sure that it was in set notation and processed the 2, the 5, 0, 4, and 1, and there is the values that we get there. And then right after that, we have to do our output values. So our output values, if you remember, are all of your y values listed in set notation in numerical order. But again, we can't have any repeats when we list our output values. Repeating output values are allowed. We just don't write them within our list of our output. What is not allowed is repeating x values. If these x values repeat when we are processing your relation into your list of input values, that tells us right away that this is not a function. Your input values only can go to one unique location, exactly one output. Therefore, if your x, when you're writing that input list down, repeat, I know automatically it's not a function. But in this case, this relation has no repeating x values. When I wrote my list, I noticed that. But when you do your output, you can see that there are repeating. Y values are allowed to repeat. We just don't write them when we process the output. So again, you can see that within our relation, we have repeating 3s, but when we write that list of output values, we only represent it once. Now, once we have listed our input and output values, we move on to a different type of drawing that was called our mapping diagram. In that mapping diagram, it's made up of 2 ovals. The left oval contains our input values vertically in numerical order. Our right oval represents our output values vertically in numerical order. It really helps by listing your input and output first from your relation in numerical order, so your mapping diagram is a little bit easier to create. Once we have the input and output listed in each oval, then we go through our mapping process. We go to the first ordered pair in our relation, and we know that 2 as an input value gives 3 as an output value, and that's when we connect 2 to 3 with an arrow. Please make sure that the arrow ends at the output value. Then we go through our 5, 4, our 0, 3, our 4, 1, and finally our 1, 2. That mapping diagram helps me process as well if this relation is a function. And I can look down the first oval, which is a list of input values, and I can see that I have one map. It's going to one location. And since each of these input values have exactly one mapping output, there's one line arrow out of each of these, then I know that this does represent a function. It's a different way of looking at it. I could look at the input values and see the input values don't repeat, therefore it's a function. I can see in the mapping diagram that each of these have a singular arrow out. That again represents a mapping diagram. So we have many different symbols within our processing of a relation to see if it is a function or not. And now looking at this one, and we've checked it, make sure all your x values are unique, and they are. So we would say yes, this relation is a function. Now that's a quick review of what we did in the last lesson, and you have notes on that, but I just wanted you to hear it one more time before going into today's lesson, which is what are function rules? And there's a couple families of functions, and we're going to look at those. I'm going to give you 3 of those families because in 8th grade as well as 9th grade, there are a couple families that you're really going to study. And what defines families are your degree of your x within your equation. So it's the degree of the input value. So if the input value is just x to the first, so in your equation, which you're going to see in a second, if I just have an x to the first or just an x listed, I know that's part of one certain family. When I have an x squared, when the value is being multiplied by itself in this machine, that creates a different family. And when x is actually the exponent of a factor, that creates a different family. So those all have names. Every family has a name. So let's look at those names. And those names are the 3 function families that you're going to study between 8th and 9th grade. In 8th grade, Your linear function, this is algebra 1. So this is what we are studying in algebra 1, and then you will transition into algebra 2 next year, where you will start studying quadratic and exponential functions. So in 8th grade, we need to make sure that all of our function rules that we will be studying come from the linear function family, and that is when our x value in our equation, it has a power of 1. So let's look at those in rule form. So a linear function has a equation that looks like this, and this is the general format we use. Y equals mx plus b. And we're going to talk about that today, what the m and the b represent, and moving into future lessons, because really that's the study of 8th grade. But you can see the output is equal to a number times the input plus or minus a constant term. So this is what we're looking at. You can see that that x, it has the power of 1. So therefore, this equation follows the linear function family. Our quadratic family equations look a little different. You'll see it still starts y equals, but now you will notice there's an x squared term inside my equation. This x squared term creates this function rule to be part of the quadratic family and not the part of the linear family. Even though the quadratic family does have an x here, the x squared is the king of the equation, if you want to think about it. The highest power of x, the largest exponent, is the family it belongs to. And then exponential equations, you are going to see those start y equals as well, but then that x is an exponent of a factor. And that creates a different family, which is called the exponential function family. So again, we will categorize which family these belong to, if it's a quadratic family or exponential family or linear family, and then we're going to move on in the remainder of the year and really study those linear function families of y equals mx plus b. That's our goal to transition you into high school next year. So let's look at our function rule y equals mx plus b. So we're looking for all of the rules that fit into that format. So let's look at some examples here. Remember, the degree that you need is x to the first if the variable is showing its exponent, or just x when it's not showing. Those are all members of the linear function family, and those all come in the format y equals mx plus b. So those are the ones we are looking for. So let's try. Does this equation follow the same form that we see before us, y equals mx plus b? Yes or no? Hopefully you all said yes. This is in the proper format. I have a y equals. I have a number being multiplied by x. Therefore, 4 would represent my m, and that b term would be represented by -7. So yes, it fits into the same mold as linear function equations do. Therefore, this is called a linear function. Let's try another one. Is this a part of the family of linear functions? Hopefully you said no, and you can see within there that your equation has a cube. Therefore, this cube does not fall under the pattern of x to the first. So therefore, this equation is not part of our linear family. It's actually part of a cubic family, which you will learn more about in high school. Let's try another one. Does this fit into the mold? I'm assuming most of you said no, but it actually does. So let's look to see how it could. So y equals mx plus b. And my equation says y equals 12. So that 12 is my constant term, and it looks like in this equation, I don't have a variable term. Well, what would m have to be for me to lose this full term? And the answer would be 0. So if I had y equals 0x plus 12, what is 0 times x? Hopefully you know that that's just 0. So I would have 0 plus 12, and a simplified equation would just read y equals 12. So even though this doesn't seem to have an mx, in the equation? It does. It just happens to be that that mx is a 0x. So in simplification, we wouldn't actually show it. So that was a little tricky, but hopefully you remember if it's y equals a constant term, that still falls under our family of linear functions. Let's try another one. All right, so here we have y equals negative 5/11 x. Is this part of the linear family of functions or not? It is. This one has an mx term, but it doesn't have a constant. So we would assume that that constant would just be a plus 0. And in simplification, we wouldn't ever show an equation with a plus 0. So that is part of the linear family. How about this one? Hopefully you said no, since you saw that within that equation there was an x squared term. That x squared term makes it not a member of the linear function family. It actually makes it part of the quadratic family. So that is not linear. How about the next one? Did you remember that when I have y equals and it's just a numerical term? Yes, it does fit into this mold. Remember, equations don't always have to start y equals. They could end in equals y. We can read an equation from left to right or right to left. So this negative 17 equals y is very similar to y equals 12. Both of those are part of my linear family of functions. I think I have two more. Hopefully you said no. This is not part of the family. It has an x squared, therefore it's part of the quadratic family, not a member of the linear family. One more. And this one is, even though these are not in the proper format of the mx first and the b second, this is still a linear equation. It would be our job to write it in proper format, but that does not mean that you're going to receive the equation in proper format. So yes, this does have an m negative 2 term with an x singular exponent here, and then we do have a b term, which is 6. So that one is a linear function. So hopefully you're practicing a little bit more. You're seeing the difference between what is and what is not considered a linear function when it comes to function rules. So let's move on. Let me clear off this screen. Let's look at graphs. So if we know equations to be part of the linear family needs to have a x to the power of 1, what do graphs look like? So the first thing we're going to do is figure out if the graph is a function or not a function. We're not going to really zoom in on choosing the family of functions right away, but more, yes, this is a function by looking at the graph, or no, this is not a function, just like we did for relations. So there is a quick refresher that you need to remember. Now remember, if an x value repeats, then the relation is not a function. Remember, input values cannot repeat themselves. And if they do, it creates things that are not functions. You need to remember that for today. So when you look at a graph, how can you tell that the x values are unique compared to how can you tell if a x value actually repeats? Now, within a relation, you can see the number repeating. What would we have to see on a graph to understand that the x value is actually repeating? So let's look at this. So the first thing we have to do is grab a ruler or a straight edge. So if you have a corner of a binder there or a corner of a book, you can use that as your straight edge, or if you happen to have a ruler. What we're going to do is we're going to draw multiple lines that are parallel to the y-axis. So since the y-axis is vertical, we're going to draw more vertical lines that are parallel, and we're going to use those vertical lines to see if this is a function or not. So the way we do this is we draw vertical lines. We're going to identify the point where our vertical line intersects the graphed line. Here's the kicker. If your vertical line actually intersects the graph line at one point, it's considered a function. If your vertical line intersects it at more than one point, that's when it's considered not a function. So again, we're going to take a vertical line, which is going to be parallel to the y-axis. We're going to draw a vertical line right through our graph. And if that vertical line intersects the graph line in one location, then it is a graph of a function. If my vertical line intersects more than once, then that graph is not considered a function. So let's look at some examples. So this is what it looks like to be unique x values. So let me get my pen out. I'm going to draw a vertical line. So here's a vertical line. Ooh, this is really close to vertical, guys. I'm doing my best. So here's a vertical line, and I can see that this vertical line intersects my graph at one point. So that looks good there. Let's draw another one. So remember, in my thing, it says, in my direction, it says multiple lines. Got another one. So if I had a straight edge, this would be a lot cleaner here. So if I use the graph to help me with these vertical lines, do you see that all of these vertical lines, each one of them only intersects my graphed line in one location? This vertical line once, this vertical line once. Therefore, since all of these vertical lines, no matter where I draw that vertical line, it intersects once, that means this graph is a graph of a function. I have all unique x values. There is only one output for every input. So if this was the x-axis, this, let's say, is 1, then 1 has a specific output right here. This one is 2. 2 has a specific output, which is right here. Remember when we draw our ordered pairs. So all of these are unique. So to understand what's unique, we also have to look at what's not unique. What does a graph look like if it had repeated x values? And this is what it looks like. So what is the difference? If I draw a vertical line here, I can see it only hits once. It looks good. But remember, if I draw a vertical line here, wait a second, it hits my graph line once, twice, 3 times. So that really means that my x value repeats. So again, if this was the x-axis, and let's say that's 0. So let's say at -1 here. At -1, I have this -1, -4 ordered pair, -1, -1 ordered pair, and -1, +4 ordered pair. Well, because this ordered pair is -1, +4, because this ordered pair is -1, -1, and since this ordered pair is about -1, -4, do you see those repeated x values? And remember, repeated x values are not functions. -1 can't produce a 4, and the same -1 produce a -1, and the same -1 produce a -4. Not allowed to be a function. And that's what happens when you repeat x values. You stack points on top of each other. And that stack produces a vertical line that intersects more than one location. So if we can find a vertical line on a graph that shows these stacked input values, then we know that that function is not, that graph is not a function. So let's look at some examples and see what we can find. So I'm going to give you some examples that are functions and some that are not functions so you can see the difference. Quick refresher, function, when a vertical line intersects the graph once. Not a function, when the vertical line intersects the graph more than once. So twice, 3 times, 4 times, 5 times, all it has to do is more than once. So let's look at this. Here is a graph, and if I drew a vertical line, let me change my pen color. If I drew a vertical line right here, you can see that this vertical line hits here, here, and here. Since that vertical line hits at 3 locations, it is not a function. It would pass if I drew a vertical line here or here, but all you need to do is find one location within your graph where it fails, and that one location leads it to not be a function. For this one, if I drew my vertical lines, you can see no matter where I draw that vertical line, all of those vertical lines would only intersect once. This graph doesn't double back. It doesn't actually repeat any of the x values. Therefore, this is considered a function. So let's look at one more on the right side. Here we go again. So here, the blue line is our graph, and our red line is the vertical line we drew. So that vertical line, let me get my pen. That vertical line intersects once. This one would be once. I can't find a vertical line anywhere that intersects this blue graph to touch the blue graph at more than one location. Therefore, this blue graphed line is a function. But look here, do you see how this graph double backs on itself? And when it does that, it produces repeated x values. Again, not allowed to be in a function. This one does pass at other locations, but since that one location has repeated x values, the whole graph is not considered a function. So just like we did for our equation rules and what's linear and what's not linear, let's play a little game about functions and lines. Again, I'm just going to show you a couple. These are different functions that do pass the vertical line, and these are functions that do not pass the vertical line test. So you can see here's one that does. All of our vertical lines would intersect only once. Here's one that doesn't work. Oh my goodness, if I drew a vertical line, every point on that line would be considered an intersection point. Here's one that passes. Here's one that fails. Here's one that passes. Here's one that fails. So the reason why I did this is because it always doesn't have to be a straight line to be considered a function. It can be many different looking lines or graphs. It just doesn't, and it can't repeat its x values. And the four across the top have no repeating x values, while the four across the bottom have multiple repeating x values. And that's the difference. And we use what we call, mathematicians call the vertical line test. Remember, I told you these mathematicians only make up names that should make sense. What are you drawing? You're drawing a vertical line. And in that vertical line, you're testing to see if that function, if that graph is a function or not. Therefore, mathematicians called it the vertical line test. So hopefully the name helps with what we're supposed to do to process function or not function. So here we go. So does this pass the vertical line test? Is this graph a function? Hopefully you said yes, all those vertical lines only intersect our graphed line once. Try again. Is this graph a function? No, you are 100% correct. When we draw a vertical line here, we see that our vertical line intersects twice, not a function. Try again. Hopefully you remembered this was the one that we used in our example. So no, this is not a function. Yes, that is a function. A horizontal line does pass the vertical line test. Yes, that is a function. Another one we used in our notes. Not a function. It fails that vertical line test. Remember right here, fails twice. How about this one? Hopefully you said no, vertical lines can't pass vertical line tests. If I drew a vertical line through a vertical line, every single point of the graphed line in my vertical line would be intersection points. This was had infinite number of intersection points. That's way more than one. So that is not a function. And the last one. Yes, that is a function. If I draw a vertical line, it only intersects at one location. So that's how we define graphs. We use vertical line tests to see if that vertical line test touches once or touches more than once. Now, when we study linear function families, what's the difference between being a graph of a function and then more specifically, what is a graph of a linear function? So now, since you can identify what a function is and what a function is not by looking at the graph, now let's disseminate even further. If you can say that a graph is a function, now the next question is going to be, is it a linear function? And if to be a linear function, you need to make sure that you have a constant rate of change. That means as x is increasing, y is either increasing or decreasing at a constant rate. So from your study in science, a constant rate of change should help you understand what we're looking for. So here, our first one, is considered a constant rate of change. The reason why is as X is increasing by 1, it seems that my Y value is decreasing steadily. It's decreasing at the same rate. And when we fall at the same rate, we produce lines. That shows us that constant rate of change. This right here is a graph of a linear function. It passes the vertical line test, and you can see it's growing at a constant rate of change. And you studied that last year by looking at slope, that slope between any 2 points stays constant, and that constant rate of change is what produces a line on our coordinate plane. Here is an example of not a constant rate of change. As X is increasing, this is going everywhere. This is increasing, and then at this moment it decreases, and then it increases again, and then it drastically decreases. This is not constant. This is varying. And we look at things that vary, and we look at things that are constant. Here, even though this is a graph of a horizontal line, it's still staying constant. As X is getting larger, -4, -3, -2, remember reading a graph from left to right increases our X. My output is staying constant. So that's when you realize that these three right here are linear function families. This one is not a linear function, but this is a function. So your high school study will be like, oh, we'll tell you more. Well, what does this represent then? Right now, you know it represents a function, and your high school teachers will categorize that for you with more information. So again, let's look at this. Remember, the first one is a linear function. It passes the vertical line test, and it is a constant rate of change. That third one is not. The second one is, and that fourth one is as well. So that takes us to the end. You should be able to look at a function rule and be able to categorize it as linear or not. You should be able to look at a graph and categorize it into function or not a function. And even more specifically, once you know it's a function, is it linear with a constant rate of change, or is it not linear? Therefore, it would just still be considered a function by passing the vertical line test, but not specifically a linear function. So now, the end of today's lesson, you need to take a photo of your notes and attach that to your Google Classroom post to show me your engagement and participation in today's class. I will give you feedback on your answers for your Edpuzzle video and make sure that I see that you made it all the way through and that you took notes throughout it. So thanks, guys. Hopefully you feel a little bit more solid on our learning target. Remember, our learning target for this lesson was to be able to define and identify functions. And now we have many different ways to do that, as well as create different diagrams to help us with our input and output values. Again, hopefully that helped, and I will see you tomorrow for your practice day.